Welcome to the course on Introduction to Electrical Engineering, lab lecture 22 today on the bipolar junction transistor part 2. Well, we will like to discuss today of course bipolar junction transistor. Starting with application, we will talk about static characteristic of common base transistor circuit, and we will talk to static characteristic common emitter circuit, which is very usually is used, and then we will have a relation between the typically two current gain alpha and beta, which we had discussed already last time, and then we will talk about load lines for AC as well as DC for the transistor, and then we will like to discuss the transistor as an amplifier and part by numerical. Then the another part we will like to discuss of course hybrid parameters, which discuss already H parameters in the 2-port network. So, same is applicable for the transistor. So, we will like to discuss that. Then we will talk about AC equivalent circuit of transistor and limitations to the H parameters of this bipolar junction transistor. Then we will like to have a stabilizing the voltage supply, I mean for the purpose this BJT or transistor is used, and then we will discuss a transistor as a switch. I mean these are very typically application, of course in lot of application we have, then following by the numerical problems like. So, starting with again the transistor application, which we of course discussed many time in the last lecture also, that gives the motivation why really we are studying this transistor. So, starting that we say transistor is used in many places, especially like computer processing unit, I mean computing processing units, like we call it in short CPU, then memory, input output units, then display, mouse, keyboard, speaker, Wi-Fi. These are the some of the applications where in computers we are using this BJT, and the size of this BJT going to be day by day smaller and smaller. So, that in the same you can call it volume, you can accommodate large number of the transistors like. And then of course, the display unit like TFT LCD, as you can just see here, the controlling each pixel and color dot for flat panel display and adjusting the display back light brightness like. So, this is all used typically of different kind of, you can call it the transistors like. Then the storage devices like your every bit of your non-magnetic memory storage, flash or DRAM or EEPROM for volatile static RAM, they use all BJT, and every bit of your computing processing unit CPU register data and address for every bit of the math or logic for encryption and description, we use all these BJT as a basic unit. Then we have of course storage devices like typically kind of pen drive or the hard disk like microchip containing the transistors, which stabilize like 1s or 0s computer data and up to 1 TB capacity. I mean you can call it 1 million thick books, I mean you can accommodate on this typically in this hard disk, and no moving parts, meaning less energy needed for the more robust. So, it is only much smaller in size and compared to hard disk drive and magnetic tape and CD or DVD. So, here we have a memory certainly all through by the your BJT or mobile phones. I mean the transistor are part of modulating, transmitting, receiving and demodulating circuits, and of course, Wi-Fi, Bluetooth or cellular, all they use the basic unit transistor or BJT as a basic unit in all these applications like. So, it is one of the major important why application we are mentioning. This application only came probably hardly a not more than couple of decade, I mean hardly a decade old, but it has gone to you can call it popular throughout the world, like it has changed the lifestyle of the human beings like. Then the another is the Wi-Fi module, I mean just you can see, and how the circuit of Bluetooth circuit, and you can see if transistor in the circuit along with the other components. So, in this of course, we use the transistor for many purpose, not only for one specific purpose like. So, now coming to like a static DC circuits of a common base circuit. I mean static circuit means we talk it why we call it static, and we say DC circuit because that is like a constant signal, I mean maybe of different magnitude, but it is a constant signal compared to like we call it here the dynamic like the AC circuit like AC equivalent signals like. So, here it is a typical circuit for getting the characteristic of this common base transistor circuit. I mean you can just see here the base is a common, for we are applying the signal corresponding to like a in this NPN transistor we are applying a signal as a typically between the base and emitter, as well as in we are applying with respect to the between your base and collector. I mean, so that is why, because base is common, that is why we call it common base circuit. So, I mean, of course, all are transistor circuit, that is why we are not talking here of what with the transistor. So, we vary the input current I using the potentiometer R1 here, and for each value of I, we vary the output voltage CB using the potentiometer R2 here, and note the corresponding output current, collector currnt, like I mean. So, virtually for a given emitter current, we look into the characteristic between the your collector to base voltage versus the collector current. I mean, that characteristic we call it. So, you will have a several characteristic, because for each emitter current you will have a separate characteristic. I mean, as you can see here, I mean, we have a several base current, why minus sign is there, because according to the arrow it just flows into opposite direction. So, here it is a potential difference between collector and base. So, you can call it is VCB voltage we are applying here, and this is the collector current which is coming here, and for different emitter current certainly the characteristic differ, and all these characteristic of course can be divided into three parts. We already discussed that. One is the cutoff, I mean here on the closer to x axis, where the emitter current is almost like a 0, and then you have a typically you can call it the saturation characteristic, where the drop, I mean across this your VCB is very small and collector current goes high. I mean virtually you can call it collector current is and this region mainly we call it the amplification or active region. So, static characteristic for common base transistor shown here, and I direction is taken just flowing into the emitter terminal of BJT, that is why it is written in the minus emitter current, like. So, now from this characteristic there are some observation. So, from this figure it is seen that the positive value of the collector base voltage, the collector current remains almost constant. I mean, and for a given collector base voltage, the collector current is practically proportional to the emitter current. You will see collector current is going more and more, when emitter current is also going more and more for a given this your VCB or collector to base voltage, like. So, these are typically like a couple of observation from this characteristic, and we can call it here, of course, we can say what is here the current amplification factor for the common base circuit, and that is we call it at constant VCB. We can define the alpha delta C upon delta E, where the slope of IC upon I, that is the slope, what is the change of your collector current in a particular your emitter current. I mean of course, if we do not consider the sign. So, we can say as IC is lower than IE, the value corresponding to this gain is your 0.92, 0.99, which we already discussed earlier, like. So, in this configuration, that is the reason we call it this notation alpha. So, alpha gain is always less than 1, like. So, now coming to the static characteristic for another configuration which is called common emitter characteristic. This common emitter characteristic is very popular, especially as a power amplifier. We discussed last time also from the table, the maximum power gain is only for this configuration. So, for this here also for a given base current, I mean which we are getting from here, typically I mean will be of course having a different you can call it the applying the commutator to different commutator collector to emitter voltage, we will note down what is the value of IC. So, for each base current we will have a characteristic between the, you can call it the VC versus IC. So, here to get this characteristic we have to vary the base current using the potentiometer, and for each value of IB vary the output voltage VC using the potentiometer, and note the corresponding output collector current IC. So, here the of course procedure to get it there, maintain the base current constant a particular value, but of course, you have to repeat the many base current value and note down the collector current, that is IC for various values of collector emitter voltage which you are varying it. But that is the, you can call it typically a independent variable, and IC is the dependent variable, because that IC will be decided by the characteristic of the transistor, like. So, test being repeated for several values of base current, I mean IB, and the results are shown here. Typically, so from here this is the kind of, you can call it the base current versus collector current, and for here for a given VC, beta is typically delta I upon delta IC upon delta B, and the slope of this, and this value of the beta in generally from 20 to 200, I mean like or so. So, you can call it like this gain is much higher, I mean in this current gain in this configuration is much higher than the typically the previous one, like. So, now coming to the 2 p-n junction of the BJT can be independently biased to result in 4 possible transistor operating modes as summarized in the table. So, we can call it here we have a you can call it emitter base bias, collector base bias and operate the kind of operating mode. So, if in typically in this case we can say if emitter base junction is forward bias and collector base is also forward bias, both are forward, which we discussed last time. So, the transistor operate in saturation region means the drop in the you can call it the VC is only very small. I mean it goes to in saturation and current decided by external circuit in the transistor like. And but if both are reverse bias, emitter base and collector base junction both are reverse bias, then we call it cutoff. It means that work as a switch is off. I mean here switch is on. And if it is a emitter base is reverse bias and collector base is forward bias, then it goes like a typically as a inverse mode. And when it is a emitter base is a forward bias and then your collector base is a reverse bias, then it become a linear or we call it the active region for which we have calculated the current gain like also. So, these are the typically the modes of your operation of this BJT of this 2 p-n junction diode which we discussed it. And this is the typically the characteristic which we were talking about, that we have a collector current versus the VC for this common emitter configuration. And here again we were mentioning that this is the saturation, the shaded portion where the I just mentioned it, the VC saturation is very small, maybe depends maybe 0.3 volt for the silicon transistor 0.3 volt, but current is going to be quite high. So, it's even for depends on the how much the your emitter current base current you are just putting here the different value of base current. So, this is and when base current is 0, you will find this is we call it the cutoff region. Here in this only leakage current flows into that. And this region we call it the active region, and you can understand this active region means in the sense that you are getting like typically the collector current in proportional to the your base current. That is the region we call it as a active region, and this is certainly you can call it in this case the current gain is quite high, as that is the region we call it like in this case your power gain also very high. So, maximum collector current flows and the transistor acts as a closed switch from the collector to emitter terminal. And so, first region is the cutoff region and operation near the excess voltage, this is the cutoff region typically here where the base current is 0 and you will have a typically almost negligible collector current even if you have a different voltage applied to VCE. So, since it works as a open circuit, so we call it like a this is the cutoff region. So, operation near the voltage axis of the collector characteristic as it is a shaded portion here, and the transistor act much like an open switch and only leakage current flows through this operation and it is shown here like also. So, the second region is active region, this is the major region, it is region written here or we call it linear mode, and the operation in the region in this to the right of the saturation and above the cutoff, and in means saturation means from this side and cutoff means this side. So, this is the region here typically, and in this region the nearly linear relationship exists between the terminal current. And now, inverse mode, a transistor is reverse active mode conduct even amplifies, but the current flows into opposite direction. So, inefficient active mode with the emitter and collector base interchange, and the downside to reverse active mode is the beta R is much smaller than the your typically the your normal active mode like. And this is something like modes of operation which we are talking here. You can call it is a forward active mode where you can call it the collector voltage is the highest and the base and emitter. Emitter is almost like typically we call it count. So, this is the forward active mode, and we have a saturation mode where you can call it the base voltage is larger than typically the your collector voltage as well as from emitter voltage. So, you can call it since that is why we call it like VC is much smaller than even BB here. So, this is saturation where it work as a switch like and in this mode cutoff means where the your emitter voltage is higher than base as well as the your collector voltage is also higher than the base. It means both junctions are reverse bias. So, this is cutoff region. So, switch is off, here switch is on, and this is the forward active and this is the reverse active where you can call it like a typically your base voltage is in between again the emitter and collector voltage. So, these are the 4 modes of operation. For working this transistor as a switch, we operate in saturation and cutoff. Cutoff means circuit is open, saturation means circuit is closed and the current is decided in the circuit by external means, because saturation means ideally you must have a voltage 0 across the switch, otherwise the losses in the switch will be very high. So, in saturation, since voltage drop is very small like 0.3 volt order of that, and it means it will not have a much losses, but in active region certainly you will have a reasonable voltage across VC. So, device work as in a active region. So, this we use normally for amplification. These are used as a switch in many typically power applications, power electronics applications. There we use this as a transistor as a switch like So, this is something typically for both the transistor NPN, that was the table for NPN and PNP in generality there. So, that was for NPN only. So, voltage relation means if VB is in between V and VC, then it is active, but here it is reverse for PNP, because the just it goes reverse, and if VB is let us say greater than V or V and typically greater than VC, then device in saturation. You can call it like a typically both junctions are in forward bias, and of course, for PNP it will be cut off, and VB if it is let us say less than from VE as well as VC, then it goes to cut off, that is a switch is off. Of course, for PNP it is a your saturation, and of course, VB if it is in between the you can call it V and V, it is a reverse active, and then here it will be PNP for active zone. So, these are the modes of operation for both the transistor configuration like NPN as well as PNP. We cannot generalize this typically, because their biasing is typically corresponding to the voltage applied for NPN and PNP is different like So, now coming to the relation between these two current gain alpha and beta. Of course, we already discussed that these current gains are for also sometime different configuration. So, talking about this again common emitter configuration, which we told that is very commonly used here, and in this case of course, you can probably get the characteristic as we discussed static characteristic, that you can apply for different base current, you can just apply the different collector voltage. You can call it these are the two independent variable, and the collector current is decided by how much is the typically the base current as well as how much you are going to apply the your VC, typically your VC from this. So, now from this circuit we can call it the your emitter current is the sum of your collector plus base current, or delta E is equal to delta C IC plus delta IB, and we have here alpha equal to delta IC upon delta E, and that is delta you can say IC upon delta IC plus delta IB. So, it means this gain is certainly less than 1, because here delta IC is appearing both, and delta IB even if it is a smaller, so this will cause the alpha equal to be less than 1 like, and you can put the value of 1 upon alpha equal to 1 plus delta IB upon delta IC, or 1 upon alpha equal to 1 upon 1 plus beta. This we call it the collector divided by base current. That is the kind of application we call 1 upon beta, and from this relation we can get alpha equal to beta divided by 1 plus beta, and we can say or beta equal to alpha divided by 1 minus alpha. So, alpha is slightly less than 1, and that is the reason you can call it, if it is alpha slightly less than 1, this denominator quantity will be very low compared to the upper one, maybe 0.9 to 0.99, and this is you can call it like it will be 0.01 to 1. So, you will find the beta will be quite large. So, a small variation in you can a small variation in your alpha will correspond to the large variation in the beta as from this expression. This is getting double kind of amplification virtually correspond to because of 1 minus alpha. So, that is typically, so in the absence of input signal, when your I is 0, that is we call it like a cutoff, and we find there is still a small collector current, and this is a leakage current ICBO crossing the reverse bias collector base junction, and therefore, the total collector current is IC equal to alpha E plus ICBO, and therefore, we can see IC equal to alpha IB plus IC plus ICBO, and from which you can say IC if you take on other side IC. So, it will be 1 minus alpha equal to alpha IB plus ICBO, or from here you can find out IC will be equal to alpha upon 1 minus alpha into IB plus ICBO divided by 1 minus alpha, or from which you can get IC equal to beta IB, and this is typically the value beta plus ICBO divided by 1 minus alpha. And if ICBO is very small, then the large term of this expression can be neglected. So, we can say the relation reduces to beta equal to delta IC upon delta IB, and the leakage current is the temperature dependent, hence an increase in temperature causes the leakage current to rise. Now, coming to the load line of for a transistor, I mean the load line of the transistor, of course, typically we can again get from the typically by doing this NPN transistor with again taking with the common base configuration with amplification and with the typically the load resistance R here. So, in this case also we can think about typically, I mean the here it is a you are using a typically a AC input voltage along with the bias here, the DC voltage with the input resistance, and then you will be looking the output here corresponding the in the output alternating voltage, and this certainly this capacitor will block the your DC voltage, like I mean because this is something bias why we are to provide and why capacitor is providing here, and these are also means you want to typically get kind of amplification of the your this AC small AC signal to the towards the output, like. So, this is here what we are talking about the kind of load line. So, in this case, I mean in this configuration this voltage between collector and base we are applying, because base is a common base transistor configuration. So, this is a VCB and here we have a collector current, and of course, for different emitter current, I mean this will be that will cut of your resistance will have a different amount of the current will be cutting on the different points, and this joining these point we call it this as a your load line. So, load line is the locus of the variation of collector current for any variation in emitter current, and the straight line PD drawn is the load line and the inverse of this which is equal to the resistance of the load, like I mean inverse of this means typically because this will be having a kind of a negative slope. So, we have to take inverse of this, that we call it typically the load line, and you can just see here I mean what we have a typically load line. I mean this is the same circuit what we are showing here, and you can see the biasing in the sense that all the time the typically current remain positive, and that current why this collector current remain always positive, because we are providing a kind of bias here, like. So, this is a collector current and this is the voltage between your collector and base, and you are getting like a different characteristic, and of course, when you apply the AC signal you will find the in the output also amplified signal corresponding to this IC typically the IC current, but which have offset will go because of this capacitor, like. So, with the AC source S is off, bias point D typically here is obtained, I mean that is when you do not have a AC, that is virtually these two corresponding points here. As you can see, this point is corresponding to this point only on this characteristic. So, we can say IE emitter current will be equal to minus B1, I mean like typically minus BB, that is the voltage, minus VBE, I mean the voltage of this transistor junction divided by RS, that is the current that will be deciding. If it is a 0, what will the you can call it the emitter current that will be flowing corresponding to that. So, it will be your minus 1, because 1 volt is shown here, minus 0.7, that is the your VBE voltage divided by 100. So, it becomes minus 3 milliampere, I mean, and with the AC source on, the input current I varies between minus 1 to minus 0.5, that is virtually from minus 1 to 0.5 it is varying, and it will be varying on over this going to be increase and decrease as it is going to be in this manner, like I mean over this. So, if you go this point to this point, it will be moving from here and coming back, and on this side it will going up and coming back in this manner. So, that is the way how you will be getting on this characteristic of this load line, and you will be getting certainly I mean the typically output voltage which will be of this shape, because you will get a voltage kind of a AC voltage with a DC offset, but DC offset will go out because of the capacitor. So, you will get AC voltage output here which is amplified of this corresponding to that gain I mean of this voltage. So, you have this small voltage, you will getting reflected amplified voltage in the output, like also. So, we can call it the function of capacitor is to eliminate the DC component which I mentioned here of the voltage across the resistance from the output voltage, and if IC is the RMS value of AC component of the collector current, then ICR is the RMS value of AC component of the output voltage, and IC square give the average output AC power. And note that the lower case subscript IC indicate the RMS AC value corresponding to capital subscript IC for the DC value. And the supply voltage and resistor bias a transistor, they establish a specific set of DC terminal voltage and current, and thus determining the point of active mode operation called the quiescent point, typically constant point, and using the quiescent point is unperturbed by the application of a small signal to the circuit, and hence T is the typically called quotient point. So, your characteristic will be moving over this, as you can see here how the IC is moving with the kind of the offset in this case like. Well, so now we can call it why biasing is there. So, BJT biasing is in common emitter configuration. I mean, we just already mentioned that common emitter junction is very common, and you have a typically kind of biasing here, as you can see in this figure. So, only a DC supply VCC is needed to establish the active mode of operation, and usually quotient point of active mode of operation are unchanged by the application of AC signal to the circuit here, because you already have a corresponding to this resistance as a potential divider. So, you will having some DC bias already for applying here along with the input signal here, that will be added or subtracted according to the, you can call it the for the AC signal like also. So, here you can just see this is the your circuit, and you can calculate from equivalent of this how it really behave here. So, you will have a RB which shown here, it will be RB will be two parallel resistance, equivalent parallel resistance. If you talk about in between to this, so it will be R1 into R2 upon R1 plus R2, and the VB which will be the kind of a bias voltage which will be coming here, it will be certainly the voltage drop across the R1 out of this. So, it will be whatever current is flowing here, if we consider this current is to R1 upon R1 plus R2, that is the current multiplied R1, that will be the voltage appearing into the VC as a kind of potential divider here, and the resistance in series, and this voltage becomes, you can call it almost like a Thevenin equivalent of it here, and then you have a like RC as well as RE in this circuit. So, this is with typically with this kind of biasing here, and now you can say typically here IEQ, I mean the current flowing into here will be beta plus your IBQ, I mean like here, and VBB will be your IEQ beta plus 1 into RB plus VBQ plus IEQ into RE. I mean this circuit, if you take the total circuit, that will be the circuit here what is shown here. So, you will have a typically this voltage here, then this is typically equivalent gain corresponding to the transistor here, and then you have a the voltage drop between like your BEQ as well as the resistance there. So, this is, I mean this resistance is change equal to, it get like a RB beta plus 1 because of the transistor operation, and you get this kind of circuit finally in this case. And solving this circuit from there, you can find out VBB equal to IEQ RB plus beta plus 1 plus BEQ plus RE, and from this you can get ICQ almost equal to IEQ, that will be equal to VBB minus your VBQ this voltage, I mean in this circuit divided by your RB plus 1 upon beta this resistance plus this resistance. So, that will give you the current virtually flowing into, considering the alpha is closer to 1, means we are typically you can call it neglecting the small current, I mean of this. So, we can say collector and emitter currents both are almost equal, considering the base current almost negligible. So, if the component value are such that the RB upon beta plus 1 is much lesser than your RE, then the ICQ nearly constant regardless of the change in beta, which can change due to temperature or voltage and current fluctuations like. And now, you can call it like here the BJT biasing in common emitter configuration mode. I mean typically here again we have a here the bias means here the, I mean again you will be applying like AC signal here. So, bias point is here over this only, I mean on this load line only you will be moving. So, bias will be Q VCQ divided by ICQ, and load line will be IC and VCC minus VCE. I mean this is the typically the drop here in the transistor. So, supply voltage minus the drop will be the typically the RDC, and where RDC is the RC plus this. So, current flowing into the this network, that will be the collector current, and that is the virtually your collector current, and this is the your voltage the V your collector to emitter VCE voltage, and on which of course base current is there, and for this is for different amount of the base current like. So, this line we call of course called the load line, but of course the slope of this negative. So, it is a inverse of that, we call it the equivalent resistance of the load line. So, now typically we have here now you can call it BJT biasing in common emitter configuration, which is very much used in case of power amplification. So, coupling capacitance, I mean CC confine the DC quantity to the transistor and bias circuit, and you can call it like a bypass capacitor, that is your CC, effectively remove the gain reducing emitter resistance this for a AC signal by allowing RE to play its role establishing the beta independent biasing like typically. So, is you can call it provide the kind of biasing for this emitter junction to typically to for correspond to this resistances like or so. So, here you can call it, if we consider it that kind of capacitor biasing. So, you can call it like here, this is corresponding to the again the common emitter kind of configuration. I mean like typically, so that effect you have seen, it is not there. So, you will have a kind of equivalent circuit here. The effective resistance seen by the DC bias collector current ICQ is RDC equal to RC plus RC. We already talked about in the previous case, the sum of the both, and this will be your AC collector signal current ICC is HA, total RAC equal to, I mean both typically comes in RC RL in parallel, RC plus RL, and since RAC not equal to RDC, in general the concept of AC load line arise, I mean in this configuration like, I mean. So, you can call it now, this is a small quantity represents the AC quantity. So, VC will be equal to small IC into, you can say, into RAC, and where the small IC equal to a IC capital minus ICQ, and VC is equal to VCEQ in the circuit minus VC, and above equation can be written as IC minus ICQ equal to VCQ minus VC by RAC. That is, we call it AC load line in the characteristic. So, you have a here, you can call it the AC load line, which represents the red line, I mean, and the DC load line is typically this line, and you can understand why the difference is there, because in case of AC load line, you will have a AC quantity added with the your DC quantity, and that is the reason, I mean your AC quantity AC line will have a more the slope corresponding to these characteristic like, I mean, and of course, characteristic is same collector versus base current. So, but the question point is the same common point, I mean for either DC, you can call it the your load line, or as well as for AC load line. Of course, DC load line is only for the DC quantity, as you can see here, IC equal to VCC minus VC divided by RDC, where RDC is the sum of both the resistance like emitter resistance plus capacitor resistance. But here IC minus ICQ, that is for AC load line, because you say small means typically kind of it include the AC is a variation, I mean AC component into it, that will be ECQ minus VC divided by RAC, and RAC is typically your parallel RC in parallel with the RL like, I mean also. So, this is the difference between the your AC load line and DC load line. Now, coming to transistor as an amplifier, which are used in many applications, of course, for low power applications. So, here we can say transistor as an amplifier, that we have a DC supply, we are giving a input signal, a small AC signal means most of the signals are normally changing with respect to time, which we have to amplify, maybe like a sound in amplifier you might have seen, those are the signals, because your signal intensity go on changing with respect to time. So, we can say those signals are your normally AC signal with the, of course, with the kind of DC offset, and the output signal which we have to amplify, that should be also AC, but of course, we have to provide the bias on the both side like also, so that transistor work only in the your positive side only. So, the transistor is required to operate in unidirectional, which I mentioned only in active linear mode. So, otherwise the negative part of the AC will cause say to the emitter bias junction to reverse bias and to disturb its operation, and this will prevent the normal transistor action, means in active region it will go out of active region. As a result, it is necessary to introduce the DC bias and to bring it entire operation always into the, you can call it in the DC operating mode, so that it work all the time as amplified mode only. So, basic action which I already discussed it, the basic action of an amplifier is the input signal controls the amount of power that the amplifier takes from the power source and convert into the power into the in the load, and by connecting the load effectively between the collector and the common terminal, the transistor can produce a gain, and the transistor required to operate in a unidirectional. This is important, which we mentioned in to bring it in active or linear mode. Otherwise, the negative parts of this AC will cause say the emitter base junction to go to reverse bias, and it will come out of, and this will prevent the normal transistor action occurring as amplifier, or you can call it in active region. As a result, it is necessary to introduce a DC bias in the this transistor operating as a amplifier, because most of the signal we just amplify, they changes with respect to time. So, we consider that as a will have a almost like a AC signal, I mean like of course, with varying, and you can just see here how really we work out. So, we have a input AC, we have a capacitors on both the side, coupling capacitor, and with the of course, biasing from the your supply voltage to the base also, as well as this your resistance between the line to collect to limit the current virtually when the transistor goes towards, I mean kind of amplification. So, this is a common emitter normally amplifier which are very much used for as a power amplification. We have seen already from the table for all three configuration, common base, common emitter and common collector. So, this is the configuration which provide the highest power gain, and normally we use this as a transistor amplifier to amplify the input signal to the output signal. So, it is called common emitter configuration, since emitter is a common reference to both input and output terminal. Input is your base and output is your collector, okay. And the emitter is usually the terminal closest to the ground potential, and amplifier design using connection of common emitter has high gain for the current and voltage rating. That is the reason your power gain is also high in this configuration. So, the purpose of component applied here, the resistor RB is included to provide the bias current to the base of the transistor, and the input AC signal is fed into the transistor via C1, which prevents the signal source having any effect on the steady component of the base current or DC component of the base current, and the coupling capacitor C2 prevents the load from affecting the steady condition of the collector current, and the capacitance C1, C2 are selected to ensure the reactance is negligible at the operating frequency, means they do not take any much drop of the at the operating frequency, like they behave like a very small, they are supposed to only the block the DC, but the AC they will not block any. So, their value should be reactance corresponding to that should be almost negligible or very small, like as far as AC signal is concerned. So, let the IB the steady base current, usually termed as a quiescent current, and let the your B be the quiescent base emitter voltage, then Vs supply voltage will be IB RB plus VBE, and from where we can get the RB equal to Vs minus VBE divided by IB, and only VB the significant is smaller than Vs, and approximately RB will be Vs upon IB, because that is the bias resistance from the supply voltage towards the base junction, where the input signal is applied. So, you can call it the, you are going to add the, in addition to the input signal, you are going to add a DC signal because of this biasing provided by this RB resistance from the supply voltage, and that give another component of, you can call it the IB base, or you can call it bias current, a DC bias current in addition to the AC signal. So, let the applied signal to the is in general as approximation. It of course, it can be time varying signal, but let us consider as AC signal IB equal to IBM sin omega t, where the total base current will be now IB, that is the bias current which we found out because of RB resistance from connected from supply plus IBM sin omega t, and at any instant VCE will be now Vs minus IC RC, that is the drop virtually because of the AC current coming into the your collector resistance. So, IC will be from this will be your minus Vc by Rc plus Vs upon Rc. So, here also you will find, you are almost providing a kind of a again the kind of DC bias here, and then you can just see the same circuit here. So, you have a bias here the base which give you a DC component, this comes an AC component. So, transistor we have like all the time with the bias always in the unidirectional mode as far as the operation is concerned. So, that it work like as a amplifier, and here also you are getting typically the kind of voltage which is as amplified, but this capacitor takes the blocking the DC voltage. So, you get AC voltage, but the reactance of this and this for this signal and this signal input signal the corresponding to that frequency reactance is almost negligible here, and this is you can see this is typically the collector current corresponding to the net current AC and DC current, and this is corresponding to your the drop typically the your VCE, the drop corresponding to the the voltage drop of VCE, and on this Q is the quiescent point where only the DC signal is flowing, but over it you will have a AC going to be down, but it remain always the positive, and similarly upper side also goes and down over the quiescent point. The AC signal will be moving on this load line, and that we call it like a typically the load line for the bipolar transistor amplifier like. And here of course, we can say the load line corresponding to IC equal to Vs minus Vc by Rc, and that is the typically load line of this collector current and the your base you can call collector emitter voltage in this circuit. So, bias quiescent point will be because that is corresponding to like almost a DC only on this point. So, IB will be Vs minus Vb upon Rb, that is the biasing we are providing from bias resistance from supply voltage, and this will be almost like be your because that voltage drop is very small corresponding to the base to emitter junction. So, it will be approximately equal to Vs upon Rb, and with the input AC source on the input base current will be your IB plus IBM sin omega t. This is a very small signal adding the IB. So, we presume that this voltage will be always this current will be always the positive current. So, that it operates all the time with the DC signal only. I mean, of course, with the kind of pulsating current over the your IB here. And the operating point corresponding to this signal will be varying from A to B, and keeping safe that it does not go to 0, it does not go to cutoff region, or it does not go to out of amplification also on upper side and lower side. So, it remains still an active region as amplification. Then only, I mean, so IB accordingly we have to see what is the input signal, and accordingly we have to decide this bias current like IB, I mean, which we have to decide through the, because of this your RB resistance in this circuit to operate this satisfactorily as a transistor amplifier like. So, now coming to this as a current gain is GI, that is delta I upon delta I0 upon delta I, and that is ICA minus ICB divided by 2 IBN, and this will be voltage gain will be GV equal to delta V upon delta I, that is the output voltage which we are talking about, and this is the output current going to be in the output, and then power gain will be PO upon your PI, where PO is the signal power in the load in the output, and the PI is the signal of the input to the typically to the from the signal to the this amplified transistor circuit like. So, we can call it now it follows GP power gain will be equal to voltage gain and multiplied current gain, GP equal to GV into GI, and we can say the characteristic lying IC to IB known as a dynamic characteristic and can be derived, because why it is dynamic, because signal go on changing with respect to the time for a given value of RC and VH as shown in the figure here. Typically, this is IB and this is IC, that is the characteristic in the amplification. We make sure that this operates only in the this linear region, that is the region we call it is a active region, and transistor work as a amplifier. So, this we call it dynamic characteristic, and in which it is gone operating like. So, if a resistor RL was connected across the output terminal here, then the total load presented to the transistor amplifier will effectively RC and RL in the parallel, and the effective load you can call it RP will be RC into RL divided by RC plus RL, because that will be also responsible to decide now typically the your deciding the collector current and flowing into the typically into the load resistance. So, note that the question point is the same for both the load line associated with the RC and the load line associated with the RP, and the load line associated with the RC is termed as a DC load line, and while the associated RP with is with the AC load line, because that is giving the AC signal to the typically the for the load in the sense. So, transistor now coming to as a amplifier, we have a three region. So, first is the active region where VB junction is forward bias, because you are giving the signal to make this as amplifier, and VCB junction is reverse bias, because you are providing the kind of reverse biasing and can be applied for the voltage current and power amplification, that is the for the purpose we use as amplifier. And the saturation region which work as a closed switch. So, VB and VCB junctions are forward bias, and then the value of IB and IC are high, and the value of VBC is small in the saturation, it is much smaller than the drop of the diode, that is only normally we consider it is only 0.3 for the silicon transistor, and suitable region where the transistor is operating as a logic switch as a just close, and not a suitable for region for amplification, because here the current gain is quite small like. So, cutoff region where the region below IB equal to 0 microampere and is to be avoided if the undistorted output signal is required, and B junction and CB junction are both are reverse bias with IB equal to 0, IC equal to not 0 during the condition. So, IC equal to ICO. So, this is the three region as when transistor operate as a amplifier like. So, now coming to the typically the kind of numerical problem. So, taking first numerical problem in the given circuit, the silicon transistor has a beta equal to 75 and collector voltage is Vc equal to typically here 9 volt, then the you can find out the ratio of RBRS. So, given condition is Vc equal to 9 volt. So, we can say 9 typically minus 15, what will the typically the here divided by RC equal to IE, and that is 9 minus 0.7 divided by RB will be IB. So, from IB IE upon IB will be 6 into RB RC into 8.3. So, from here we can get a beta plus 1 equal to 6 into RB upon 8.3 RC, that is RB upon RC equal to you can call it typically order of 105.13. So, coming to the question example 2, consider the circuit shown here in the figure where beta is 30 and the ICBO is 20 nanoampere and the input voltage is 5 volt. Then the transistor will operating in So, we have to find out in which operating mode this transistor operating, assuming the BJT is the active region and neglecting ICBO, the leakage current. So, applying the Thevenin on the input. So, we can say VTH is equal to minus 12 into 15 divided by your 115, the voltage here the typically. So, plus 5 into 100 by 5. So, it will 2.78 volt, and RTH, that is the biasing typically correspond to here. So, 15 in value of 100. So, it becomes 13 kilo ohm. So, you will have a now typically equivalent to the circuit here. So, we have IC equal to beta IB. So, IB beta will be 2.78 minus 0.7 divided by 13 K into 0.16 milliampere. So, IC will be from here will be corresponding to your 4.8 milliampere, and IC saturation will be 12 minus 0.2 divided by 2.2. So, that will be like your 5.36 milliampere, and IC saturation greater than IC. So, BJT active region, because this is much lower than the saturation region, means transistor is pulled into the active region. So, now coming to the example 3, two perfectly matched silicon transistor are connected as shown in figure, assuming the beta of the transistor are very high and the forward bias voltage drop is the diode to be 0.7, the value of current I is in this case typically. So, you have a 1 kilo ohm with the diode and 5 volt, and minus 5 volt is typically bias on the other side. So, we can say since both the transistors are similar, so VB equal to VB2. So, IC1 will be IC2 e to power VB minus VB2 divided by VT, that is equal to 1. So, beta for both are same. So, there say we can say I beta 1 equal to IB1 equal to IB2 equal to IB, and applying the Kirchhoff law we can say IR equal to 0.7 minus 0.7 minus in bracket minus 5 divided by 1 K. So, it is 3.6 typically milliampere, and typically correspond to applying the Kirchhoff law at the point P here. So, we can say IR equal to IC, typically the current plus 2 IB, the current which is going to be will be the total current. So, IC plus 2 IC upon I beta, that is typically IB, and this will beta plus 2 by beta, that is IC, that is IR, and beta is very large. So, we can say IR equal to RC equal to 3.6 milliampere like. So, coming to example 4, the transistor in this given circuit should always be in active region, taking VC equal to saturation 0.2, VB equal to typically your 0.7, the maximum value of RC in which it can be used in this circuit. We have to find out the value of this RC, so that it operates in always in active region, and beta is given typically here already 100 like. So, all parameter there. So, applying the Kirchhoff's law, that is 5 minus 0.7 equal to 2 kilo ohm into IB. IB comes 4.32 K, that is 2.15 milliampere, and collector current IC equal to beta into IB, that is 215 milliampere, and applying the Kirchhoff voltage. So, that will 5 minus 0.215 RC equal to VC. So, from here you will find the VC is greater than 0.2, and from which you can put the value 0.215 RC equal to less than 0.5 minus 0.2. So, RC comes supposed to be less than 4.8 0.215. So, RC should be therefore minimum value of RC typically from this will be 22.32 to pull it into the active region like. So, now coming to question example 5, a BJT have alpha equal to 0.98, IB equal to 25 microampere, and ICB equal to 200 nanoampere. Find the value of DC collector current, the DC emitter current, and the percentage error in the emitter current when the leakage current is neglected. So, we can say alpha equal to 0.98. So, beta from which we can get alpha upon 1 minus alpha, that is 99, and from this we can find IC equal to beta IB plus ICB upon 1 minus alpha. So, it becomes 2.495 milliampere, and DC current, the emitter current follows from here I equal to IC by ICB divided by alpha, it comes 2.518 milliampere. So, neglecting the leakage current, we can say IC equal to beta IB, that will 99 into 25 microampere. So, it becomes 2.475 milliampere, and I will be IC upon alpha. So, it becomes 2.475 milliampere divided by 0.99. So, it comes 2.5 milliampere, and emitter current error will be your typically 2.518 minus 2.5 divided by 2.518. So, its error comes 0.71% only. So, now coming to example 6, in the circuit shown here of this transistor with the emitter configuration. So, beta is 100 and IBQ is your 20 micro ampere, we see like your 15 volt, and RC is 3 kilo ohm and ICBO equal to 0. Find A IEQ, B VCQ and C find VCQ if RC is changed to 6 kilo ohm and all else remains the same. So, from this we can find out alpha equal to beta upon 1 plus beta. So, that comes 0.9901 and ICBO equal to ICO equal to 0. So, we get ICQ equal to beta ICBO, that is 2 milliampere, and IEQ will be ICQ upon alpha. So, it is 2 milliampere 0 divided by 0.9901. So, it comes 2.02 milliampere. So, from application of Kirchhoff's voltage law around the collector current, so we can call it VCO equal to VCC minus VCBQ equal to VCC minus ICQ or RC, and that is 15 minus 2 milliampere into 3 K, that comes 9 volt, and ICBQ is unchanged, then the CQ is unchanged. So, VCBQ will be VCC minus ICQ RC, that is 15 minus 2 milliampere into 6. So, that comes only typically 3 volt. Now, coming to example 7, a PNP silicon transistor circuit shown here, we have a RB equal to typically 500 kilo ohm, RC equal to 2 kilo ohm and R equal to 0, VCC equal to 15 volt, ICB equal to 20 microampere and beta equal to 70. Find the quiescent point collector current. So, here as a solution ICEO equal to beta plus 1 into ICBO, that 70 plus 1 into 20 microhenry, that comes 1.42 milliampere. And now, applying the KVL loop in this case. So, VCC will be equal to BBQ plus IBQ RB. Typically, here that IBQ will be VCC minus BBQ upon RB, and that is 28.6 microampere, and ICQ will be now beta IBQ plus ICBO. So, that comes 3.42 milliampere. Now, coming to example 8, the silicon transistor of common base configuration, circuit has alpha equal to 0.99 and ICO equal to 0, and also VE equal to 4 volt and VC equal to 12 volt. If IEQ equal to 1.1 milliampere, find the RE, the resistance here, and if CQ is minus 7 volt, find the RCC value typically of this resistance here by applying the Kirchhoff about the emitter voltage loop typically here. So, RE will be VE, that is the voltage here, plus VBQ divided by IEQ. So, that will be 4 plus minus 0.7 divided by 1.1, that comes 3 ohm, and by KVL around the transistor terminal. So, VCBQ minus VCBQ minus typically VBQ, that minus 7 minus 0.7. So, it comes 6.3 volt, and with the negligible leakage current we can say ICQ will be alpha IBQ, that is 0.99 into 1.1 milliampere. So, it comes 1.089 milliampere, and by applying KVL around the base collector current on other side. So, RC will be VCC divided by VCB by ICQ. So, that comes 5.234 kilo ohm. So, coming to example 9, the silicon transistors in differential amplifier mode, as you can see here, has a negligible leakage current and beta 1 equal to beta 2 equal to 60, and also RC equal to 6.8 kilo ohm, RB equal to 10 kilo ohm, and VCC equal to V equal to 15 volt, and find the value of RE needed to bias the transistor such that VC EQ equal to VCQ equal to 8. So, by symmetry we can call it IEQ equal to IEQ 2, and by applying the KCL we can say I equal to IEQ plus IQ 1 equal plus IQ equal to 2 IQ 1, because both are identical, and we can say using the loop voltage we can say VE equal to IBQ RB plus VBQ plus IQ RE, and from this equation we can find out the ICQ equal to beta plus 1 by IQ, applying the KVL around the left loop. So, VCC plus VB equal to beta 1 plus 1 IQ 1 plus RC plus VQ 1 plus 2 IQ 1 into RC, that is for typically transistor 1, and applying V equal to 1 upon beta 1 plus IQ 1 RB plus BQ 1 plus 2 IQ RB equal to IBQ plus BQ 1 plus RE IE. So, substituting 3 for this RE IQ, it result second equation to IQ equal to beta 1 plus 1 in bracket VCC plus VBQ minus VCQ divided by beta 1 RC minus RC, and putting the value it comes 1.18 milliampere, and from here RE becomes like a V minus 1 upon beta 1 plus 1 IQ 1 RB minus VQ upon 2 IQ 1, and putting the value it comes 5.97 kilo ohm. Coming to example 10, in this case of common emitter amplifier with the bias capacitor on both sides. To consider the common emitter amplifier shown here, a 2.2 kilo ohm resistive load is connected across the output terminal, and AC signal of 0.6 volt peak and internal resistance of 10 kilo ohm is connected to the input terminal. So, effective input resistance of the transistor is 2.7 kilo ohm, and determine the current, voltage and power gains of the stage. The transistor characteristic and relevant load lines are shown in the next slide. So, these are the characteristic equation of AC and DC line, of course, over the DC line, and from this we can have a calculation. So, first determine the extreme of the line. So, DC line is IC equal to 0 and VC equal to 12. So, when VC equal to 0, then IC equal to 12 upon 0.18, that is your 6.8 milliampere, and then quotient base current will be IBQ equal to 12 upon 200. So, it becomes 0.6 milliampere, that is 60 micro ampere, and for AC line RP will be delta I upon delta V upon delta I, that is 1.8 into 2.2 divided by 1.8 plus 2.2, that is typically 1 kilo ohm. So, the slope of AC load line is minus 1 upon RP, that is minus 1 milliampere upon volt through a point A, which is given by the intersection of IB equal to 60 microhenry load line and DC load line. So, from AC signal, the effective input resistance is 2.7 kilo ohm in parallel of 200 kilo ohm, and that is 2.7 kilo ohm, and peak AC current will be now 0.6 divided by 10.2.7 into 10 power 3. So, it becomes 47 microampere, and hence the maximum base current will be IBQ plus IBM. So, that is 60 plus, that is a bias, plus this AC, say 47, that is 107 microampere, and the minimum base current will be IBQ minus IBM, that is 60 minus 47, that is 13 microhenry. So, it goes microampere 13 to, typically it will be going to 113 microampere to 107 microampere will be going to the base here in this circuit like. So, now from AC load line we can say delta AC will be 5.1 minus 0.7, that is 4.2 milliampere. So, this change in collector current is shared between the 1.8 kilo ohm and the resistor 2.2 kilo ohm load resistor. Hence, the change in the output current will be delta IO0 equal to 4.2 into 1.8 into 10 power 3, 1.8 in plus 2.2 into 10 power 3. So, this comes 1.9 milliampere, and the change in the input current will be delta I will be 107 minus 13, that is 94 microampere, and current gain will be GI delta IO upon delta I, that is will be the 20 for this modified circuit. And now, your change in the output voltage will be delta V equal to delta VC 8.5 minus 4.3, that becomes 4.2 volt peak to peak, and thus the change in the input voltage given by the change in the bias emitter current. So, delta I will be delta I into RI, putting the value it comes your 0.25 volt peak to peak, and voltage gain will be GP delta V upon delta I. So, 4.2 divided by your 0.25, that becomes 17, and power gain will be GP equal to GV into GI, that is 17 into 20 340. So, that is the power gain we get it from this amplifier circuit. Now, these are the sum of similar line, the unsolved problem based on that for amplification and different mode of the transistor around typically. And now, we come to the another part of this lecture that called hybrid parameter for the transistor. For because here we are considering transistor as like a kind of a 2-port network, and we already discussed this H parameter in 2-port network. So, we can just say here hybrid parameter of BJT. Even there also we give an example kind of similar, that H parameter is normally applied for BJT circuit. So, for a small AC signal, the transistor behave as a linear device, because the output AC signal is directly proportional to the input AC signal, and under such circumstances the AC operation of the transistor can be described in terms of H parameters. And now, this is the transistor as a kind of a 2-port network, which we discussed already earlier. So, we can say for hybrid parameter V1 input voltage will be H11 I1 plus H12 V2, and I2, this I2 will be equal to H21 I1 plus H22 V2. This is the V2 here, like that is the output voltage, this is the input voltage, this is input current, this is output current, and this transistor is amplified with these two H parameters. Now, we can typically look into how this H parameters play here the important role. So, following points are worth noting by considering the behavior of a transistor in terms of H parameter. The value of H parameter of a transistor will depend upon the type of connection used in the circuit, whether common base, common emitter or common collector, and the value of H parameters also depends upon the DC bias or operating point or Q point. If the DC operating point is changed, and parameter will accordingly change. And this is the same, typically you can call it the here the H parameter equation for this transistor BJT, V1 equal to H11 I1 plus H12 V2 and I2 equal to H21 I1 and plus H22 V2. So, these are the parameters, H parameter H11, H12, H21, H22, and here we call it for common base configuration, we call it HIB, HRB, or this we call it HFB and HOB, and for common emitter configuration this is very common, you can say for amplification, it's H11 call it HI and H12 HRE or H21 HFE, and then H22 is your HOE. And similarly for common collector configuration, so it's called H11 HIC, then typically H12 is HRC, H21 is FC, and H22 is HOC, and this we normally call input impedance, that output is short circuited, and typically we call it like a reverse voltage when input circuit is open, forward current, output is short circuit, and output current, input is short circuit. This is the configuration what we really thought of two port network applying in the same manner we just calculate typically all these H parameters as a two port network, which we already discussed in very much in detail even. So, now you can just see here, this is the transistor in terms of V1 I1 and V2 I2, and with the RL and input signal, where V2 is VCE and I2 is IC collector current, that goes to typically like as a common emitter configuration. Common emitter configuration is very common for amplification. So, that is the reason we are taking an example here. So, V1 is VBE, that is the voltage which we apply for base to emitter junction, and I1 input current is the base current, and output here it is certainly the voltage of VC across the load, and the ISO is the collector current which flows in the output. And this is the, you can call it equivalent circuit into H parameters. So, here we are applying VBE volt, current drawn is IB base current, and this is a, you can call it the input impedance resistance, you can call it input resistance HIE, which we define, and then this is the dependent voltage source, H RE into VC, that is in terms of output voltage, or V2 you can call it here. And similarly for the secondary side, we have here the typically a kind of impedance, or you can call admittance 1 upon HOE, and then you have a typically a kind of a kind of current source HFE into IB. So, this becomes a like a, you can call it a as a transistor amplifier or equivalent transistor, the H parameter equivalent circuit, like where the you have a dependent voltage source, dependent current source, and this dependent current source is in terms of input current, this voltage source is dependent on output voltage source, like as we have looked into earlier two parameters like. So, from this now from this equivalent circuit in H terms of parameter of BJT, we can say VB will be HIB into IB plus HRE into CE, and typically your output current I2 or IC will be HFE typically into IB, typically this one plus HOE into VCE. So, that is typically you can call it the this is the impedance. So, it is multiplying, that will become a current. So, that becomes the admittance, and this is your typically the you can call it impedance. So, HOE this. So, these are the two equations for you can call it input voltage and output current. So, HOI the short circuit input resistance or impedance, typically HI value is 1 to 5 kilo ohm, and HRE the open circuit reverse voltage ratio, and typically this is normally HRE is kind of order of 0, and HFE is the short circuit forward current ratio, that is normally the you can call it current gain, that is order of 20 to 200, and HOE the open circuit output conductance or admittance, that is HOE here which is used here, that is order of 10 to 100 microsiemens. So, these are the typical value for the a common transistor circuit like, and the input impedance is normally Z, we can call it is a VBE divided by IB with the AC load resistance across the output port here CE. So, we are applying the KVL in the output loop, we can say HFE, IB will be equal to minus HOE plus 1 upon RL, that becomes the typically the complete admittance into the multiplied the VC, the voltage applied across here, and the KVL in the input loop will be VB minus your the voltage will be equal to this voltage HI IB, and from here you can find out the ZIN input impedance will be equal to HI minus HRE HFE divided by HOE plus 1 plus RL, that is reflected kind of input impedance here, I mean of this transistor amplifier circuit. And the output impedance Z out will be BC upon IC with the short circuit across the your input port, I mean, and the KVL in output we can say HFE IB equal to minus HOE plus 1 upon RL, that is load resistance VC, the voltage applied here, that, and the KVL in the input loop will be VB minus again HF equal to I upon IB, and from here we can find out the Z out will be 1 upon HOE minus HFE HRE upon HIE, and we can call it here typically the AC load RL across the output, because it is AC load, that is why we are talking about this as a small notation of. So, current gain will be AI equal to IC upon IB, and this AI will be HFE upon 1 upon plus HOE into RL, and voltage gain is VC upon VB, I mean like typically in the output. So, that is I minus IC RL divided by IB Zn, and that is minus RE upon ZI into AI current gain, and where the now voltage gain will be your minus HFE divided by ZI in bracket HOE plus 1 upon RL. So, now coming to AC equivalent circuit for this transistor amplifier. So, you have a common emitter amplifier which we already discussed few minutes before with the biasing circuit. I mean we have a biasing circuit corresponding to typically a bias resistance here, as well as we are having certainly the along with the DC quantity as far as in transistor is concerned. So, you have a AC signal, but we are adding a because of biasing DC signal here. So, it will be DC, and removing the DC for the output, this is the your typically biasing capacitor there takes the output. So, here we have AC, here we have AC, in between these two capacitor take care. The transistor operates always with the unidirectional signals of current and voltage like common. So, here, and this is the equivalent circuit how it is getting modified. So, you have a your input voltage with the this resistance, and then we have a bias resistance here, I mean typically coming across here across the B, and that is the same typically the gain we were talking about, and then you have a base current flowing, and on this side we have a typically the AC load in parallel the bias resistance, and then we have a same equivalent circuit of the transistor, we call it as 1 upon HA into the your current dependent source of the base current here, like this is base current, this is base current dependent current source on this side. So, that is the you can call it a small signal AC equivalent circuit in terms of hybrid parameters, and that I mean the same circuit here. So, we can say where can modify into RP equal to RC, the two resistance in RC to RL RC plus RL. So, we can call it like collector current will be 1 upon HOE divided by 1 upon HOE plus RP into HOE into IB, that is typically the current source here like I mean. So, that will be the collector current, net collector current coming here, and the current gain of transistor IC upon IB will be I equal to HOE HFE divided by 1 plus HOE into RP, and IL load current will be equal to your RC upon RC plus RL into IC in terms of this, because it is divided into this divider circuit, and II will be IB into RB plus HFE, I mean from here divided by RB, I mean correspond to this circuit, and now net current gain GI will be IL upon IE, that is GI equal to AI RC RB divided by RC plus RL and into RB plus HIE, that is your net current gain typically coming out here. And now voltage gain I mean will be here, your GB will be VC upon VB, the signal which you are applying here, minus RC into RP divided by IB HI, that is minus RP upon HI into AI. So, GP will be your minus RP HFE divided by HI into 1 plus HOE RP, and power gain will be GP into GI, GV into GI, and this is your of course AC equivalent for your common base. So, here we have a common, that is another transistor circuit, typically here we have a common base, and we have a input corresponding to emitter, and output is again corresponding to the typically the collector here, and you have a equivalent here. So, we have a equivalent circuit here, again you have a AC input with the resistance, and you have a again the bias resistance corresponding to minus voltage typically here, and you have a like HI that transistor equivalent, and here you have a typically you have a current emitter current dependent, your emitter current is the input current. So, that is emitter current dependent, you can call it the voltage source, and here you have a 1 upon HI into, that is the typically the equivalent, I mean you have a RP which is equivalent biasing and load resistance like. So, from here this is the net equivalent where you can find out collector current HOE HFP IE upon into 1 upon HOE divided by 1 upon HOE plus RP, and current gain from here we can find out IC upon RE, that is GI equal to HFB 1 divided by 1 plus HOE RP, and power gain will be GP into GI, where the voltage gain is VCB upon IB minus IC upon RP divided by IE HIP, that is minus RP upon HI into GI, and GV will be equal to minus RP HIB into 1 plus HOE RP, and from here you can get the power gain. So, this is a AC equivalent circuit of typically of the transistor amplifier. So, we can say for common base amplifier or common amplifier, so AI is a negative and there is a 180 degree phase shift between the input current and output current, and AB is the positive and the input voltage VEB is the output voltage and VCB is the out. And here for common emitter amplifier, this is very commonly used. AI is the positive and input current IB and output current both are in phase each other, and AV is negative, that is there is a 180 degree phase shift between the input voltage and the output voltage. Now, coming to the what is the limitations of this hybrid or H parameters for a transistor. The limitations of use is two major limitations of the use of these parameters. It is very difficult to get the exact value of H parameters for a particular transistor. It is because these parameters are subject to considerable variation, unit to unit variation, and variation due to change in temperature, and variation due to change in operating or quiescent point. And the H parameter approach gives the correct answer for a small AC signal only, and it is because a transistor behaves as a linear device for a small AC signal as a linear amplifier. And these are hybrid parameter variation, virtually how it is taking place for this. So, how the temperature HFE changes, HOE changes and HIE changes with respect to the typically the temperature variation, like how these parameters are affected like and this is typically you can call it like a variation with respect to the collector current. So, here you can just see here collector current is milliampere, and it's typically you can say all 4 parameters, your HFE, HIE, HOE and HRE changes, all 4 parameter changes because of this. So, these are the typically because of these limitation temperature and these limitations, these are typically the problem. So, limitation of this is for most bipolar transistor input resistance as given HIE tends to be about 1 kilo ohm, which is of electronic circuit tends to be a rather a small value, and it follows that there is always a significant input current, which have two effects. Amplification is somewhat limited, and lower levels increase the size and rating of the circuit component more than the desirable. Now, coming to the part of stabilizing the voltage supply, where we really use typically stabilizing volt. So, network which supply the steady voltage is called the stabilizing circuit, and it maintains a constant output voltage when the supply voltage varies and or the load current changes. So, we use transistor as a typically kind of voltage stabilizer. So, here assuming the supply voltage is derived from the rectified AC source, and the stabilizing circuit is usually inserted between rectifier and associated smoothing circuit as shown here. So, we have a you can call it the voltage unstabilized voltage with the typically the diode, so that it cannot have a back throw, and this is the stabilizing circuit. We want to stabilize this transistor as a you can say as a stabilized voltage output across the load. This is very popular application of the transistor as a you can call it in power supply as a stabilized power supply. So, in order to indicate how the stabilization circuit perform, we use a factor term the stabilizing factor, and if it assumes that the load required to a constant current in this. So, stability factor here is change stabilized voltage across the load and change in unstabilized voltage. So, for satisfactory stabilization S should be small, effectively small and better. One of the most simple stabilizing circuit consists of a resistor in series with the load as well as the Zener diode in parallel with the load. So, we connect across the and here we connect a typically a resistance and we connect a Zener, and that is the load resistance. So, and say stabilizing circuit. Why we connect the load, the voltage, what is the difference, it should be absorbed by this. Otherwise there will be large current flowing into the Zener like and you will get a stabilized voltage across the Zener which apply across the load. And the particular characteristic of Zener diode are that the voltage across it remains nearly constant, provided the load current remains between the set limit and the unstabilized voltage remains also within the set limit like this circuit can work within the limit like. So, the effective ness of a stabilizing circuit when responding to changes of the load current, assuming the unstabilized voltage is held constant, is indicated by the effective internal resistance of the supply circuit, that is RO, change in output voltage divided by change in output current, that is delta Vs upon delta IL. So, stabilizer which can handle better range of variation affected by a transistor in series with the resistance and this arrangement. So, this is the arrangement which normally use the your DC supply for stabilization. So, here we operate transistor as amplifier, and this is the stabilizing circuit, and we expect the load voltage will be constant here, and this is unstabilized voltage, and accordingly as the input voltage varies, we connect it as a kind of let us say base current which we amplified, and voltage across the, you can call it VCE here, the voltage across the transistor go on changing as the input voltage varies, this drop also varies. So, that the output voltage remain across the load remain well stabilized the constant. So, this is used as a transistor amplifier. Most of the your regulated power supply you might have seen in the laboratory. So, that is the basic concept why I wanted to discuss as a transistor as a kind of you can say as a stabilizer used in stabilizing circuit. So, we say stabilizing voltage supply for this is for high power, because Zener cannot work for that much power. So, current through the transistor is varied by alternating the voltage applied to the base, and the potentiometer is a cumbersome and is more practical arrangement, is a comparator network is used in which the output voltage is proportional to the difference between the two voltage, and one derived the from unstabilized source voltage, and then other is from the voltage to the load. And this is the typical kind of really a practical supply. The arrangement is shown here. Again we have a transistor amplifier, okay, and we have a output voltage here. So, we are taking as a one you can call it reference, we are generating from the output voltage which is well regulated voltage, and we consider this as a typically a proportional form voltage stabilizer, because we consider the output voltage is well regulated. So, we are taking part of this as a reference voltage, and the feedback voltage of course, we are taking from input from the this voltage with the typical kind of biasing which is unstabilized voltage to this amplifier, which from which we derive from the biasing we derive the your base current. So, that it automatically work as a kind of amplifier according to the unstabilized voltage, which not only have the DC only, but it has also AC component. So, this work as a good stabilization circuit for incorporating the comparator network. So, let us talk about how to operate the stabilizer operation. A reference voltage V Z is obtained from the unstabilized supply voltage and simply derived from a Zener diode as shown, because that is only for the circuit for just as a signal from the input to the base current only. The output voltage is applied to a potential divider of R1 and R2, and voltage across R2 is V2 and should be less than equal to V Z, and the difference between the V2 and V Z is detected by comparator network and amplified by DC amplifier. The amplifier output is applied to the base of the transistor, and if the voltage comparison shows the voltage V2 and Vz are equal, there is no output from the amplifier, hence there is no control to the transistor, and the collector current remains unchanged, and should be there the difference between the V2 and Vz. This amplified and changes the bias condition of the transistor, and this either causes the emitter current to increase or the decrease in the change in the output voltage, and this causes V2 change until it equalizes Vz, and at this point the voltage are equal and no further change occurs, and this arrangement can produce very low stabilization factor as well as a low internal resistance like. And now coming to that is a typically as a amplification we use in practical power supply. Now, this is as a switch we use normally as a kind of switch mode power supply or as a switch in many your electrical circuit. So, here also we have like again the you can call it the this as a common emitter junction transistor characteristic, that it is VCE, and this is a collector current. We have a active region, we have a saturation region, and we have a we call it cutoff region. So, considering the load line for defining as a switch means we should operate in saturation or in cutoff, and make sure that it does not go to inactive region, otherwise you will have a lot of the heat dissipation, because we are deciding the design of the switch correspond to these two region only. So, consider the load line of a transistor amplifier as shown in this, and there are two extreme conditions. When both junctions are reverse bias, there is a cutoff region that is correspond to this, and when both junctions are forward bias, there is a saturation of this like here. So, transistor as a switch here for the let us consider first as a on as a switch for saturation region. So, transistor will be biased so that a maximum amount of base current is applied, which results in a depletion layer being the small as possible, and maximum current can flow through the transistor, and this current is decided by external circuit. And we say transistor is switch on, fully on. Ideally, this should have a 0 voltage across the transistor, that we see saturation, that is normally typically a 0.3 volt for silicon transistor, and this is the typical kind of mode. Here we have of course, the you can call it the to limit the saturation current here, but it can be otherwise a kind of part of load, and this is the base resistance and base current. And here when we apply the base current, we consider this transistor goes, if base current is above a particular limit, then only it goes into saturation, and then this becomes as just only switch. There is a very negligible voltage compared to this voltage, it is a negligible voltage across this junction of VC, voltage across these two VC drop like. So, it is come a switch. The another is typically off state. So, then we can define the cutoff region of state when both the junctions are reverse bias, and VB is less than 0.7 volt and IC equal to 0. Hence, the operating condition of the transistor are 0, input current is 0, output collector current and maximum collector voltage, which results in a large depletion layer and no current flow through the device, and therefore, transistor is considered as a fully switch off. And this is the condition when base current is 0, collector current is also 0, and this considered switch is open. So, this open in your saturation means as a closed switch, we are using lot of electronic circuit or power electronic circuit as a switch. So, for all the imperfections, the transistor switch is useful because it operates effectively in the transmission of digital signal and also have a quick switching time, therefore, responding to very high bit rate, and this is typically as a transistor as a switch for amplification. You can just say LD sensor, and you have a here the typically kind of a LED diode with resistance, and how the relay is operating with this amplification. This is a relay, you will be energizing. When you switch off, this is de-energized. When you switch on, it will be getting energized, and that relay will close the switch for this your total power circuit. So, this work you can call it, this switch operates to operate the your normally the relay here typically. So, transistor used in a light operated switch for operating this from the from simple light also, that is you might have seen that how we with the LDR sensor automated switch are operated with the lighting corresponding to operating the relay of this your lamp circuit or lighting circuit like. And this is typically the kind of application, transistor operating as a relay connected to the DC motor. This is a DC motor which operate closes from the same kind of relay, that is another application. Now, coming to the numerical problems, a common emitter amplifier comprising a transistor parameter HI 800 ohm, HFE 50, HOE 20 microsiemens. The bias component and coupling capacitors have negligible effect. Input AC signal is 60 millivolt, and peak from peak to peak internal resistance for a source internal resistance of 2.2 kilo ohm, and the total load on the amplifier circuit is 4 kilo ohm. Determine the current voltage and power gains of this amplifier. This is the circuit of, we already talked about common emitter amplification with all the parameters mentioned in this equivalent circuit of the transistor typically of your H parameters, and we can just calculate all parameters. HO equal to 50 kilo ohm and IB equal to typically your 60 into 10 power divided by 2200 plus 800, that comes 20 microhenry, and the current gain comes your IC you can calculate from here, it comes by your 926 microhenry. So, current gain is IC upon IB, and it becomes like 46.3. And now, you can find out voltage gain VC upon VB from this. So, putting ICRB divided by IBRB, putting the value, it comes minus 230.1.5, and power gain is multiplication of both voltage and current gain, and it comes 10,718. Of course, these signals are very small micro ampere only. So, that much amplification is possible into your millivolt to extending to going to be the volt, 60 millivolt will be, and many you will find many sound circuit, many application your volt signal is very small, which can be amplified to the some voltage to apply for your either loudspeaker or many circuits like. So, coming to second example, the BJT parameter in the circuit are shown of this again common your emitter amplifier circuit, HI 2 kilo ohm, HOE 25 microsiemens and HFE 55. The load resistance dissipate AC signal power of 10 milliwatt, and determine the power gain of the amplifier and the signal induced EMF like. So, this is the equivalent circuit with the load resistance here as well as the input bias resistance. So, from one up you can find out to 1 upon HOE, that comes 40 kilo ohm, and the power output power is given 10 milliwatt watt, and from this you can find out what is the typically VC for across the load, that comes 10 volt, and applying the KCL there. So, you can find 55 IB equal to typically 10 upon typically here 10 power 3 plus 10 upon 10 to power minus 10 3 plus 10 upon 10 to power 1, that comes IB equal to 40.9 in 40.9 microampere, and applying the KCL for input current. So, you can have a 40.9 10 power 3 applying this. So, it become input current comes again 41.9 microampere, and input signal E you can find out now current multiply the resistance of the two component. So, it comes 0.29 volt, and from here the input power can be VBII, putting the value it comes like your 3.43 micro watt, and the output power is already given 10 milliwatt. So, power gain is P upon Pi, that comes 2920 here, I mean for this transistor. This is the configuration with common emitter, typically configuration as a power amplifier. So, coming to numerical 3, BJT is used in common emitter arrangement has the following hybrid parameter, where the DC operating point is VCQ 10 volt, ICQ 1 milliampere, HI 2000 ohm, HO is 10 to power minus 4 moho, HRE is equal to 10 to power minus 3, HF equal to 50. So, AC load line seen by the transistor is RL equal to 600 ohm, and determine the input impedance, current gain and voltage gain, and what will be the approximately the value of reasonable approximation. So, this same equivalent circuit of your H parameters of with common emitter, I mean, and the input impedance in terms of this you can find out that I equal to HI. So, upon putting the value you will get 1972, and the input impedance approximately equal to HI, that will be around typically 2000 ohm, and current gain can be IC upon HI. So, just putting the value of this you get 47, and this is equivalent to like AI equal to HF equal to 50, and voltage gain VC upon VCB, put the value it comes minus 14.5, and approximately AB is the voltage gain, putting the all the value it comes minus 15. So, voltage gain is the ratio load to the input impedance times the current gain, that comes your minus 15. So, coming to example 4, in the common emitter which is used normally amplifier, so on RC equal to RL equal to typically 800 ohm, RI equal to 0, and R1 equal to typically 1.2 kilo ohm, R2 equal to 2.7 kilo ohm that typically, and HO equal to 0, 100 microsiemens, and HF equal to 90, and HI equal to 200. Calculate the voltage gain, current and the current gain. So, in this equivalent circuit, putting the value here of this IL, so you typically L here, and then the voltage gain putting in this equivalent from here. So, you will get around putting all the parameters here with the including the load resistance. So, you get minus 173.08, and again the putting the value in IB all these. So, RB that biasing typically comes at 31 ohm, and from this relation you can find out IB. So, current gain IL upon IE you can find out from this, putting all value you come minus 34.87. So, coming to example 5 for typical common emitter amplifier, that is normally we talk about amplifier. This is the H parameters equivalent circuit of this total transistor amplifier. HI equal to 10 power minus, HF equal to 100, and HO 12 microsiemens, RL 2 kilo ohm. Calculate the current gain, voltage gain, and input impedance, output admittance, and thus the characteristic of impedance, typical common emitter amplifier. So, here for this transistor amplifier for common emitter, these are the output current relation, the current gain, I mean putting the value of this current gain. So, we get current gain minus 97.7, which is approximately 101, and then from this to find out voltage gain of this we already derived the relation, putting the value it comes 199.2. So, this we can say approximately 200, and then the typically eliminating the value. So, just putting the Z in, putting in the formula all the data given here. So, we get 980.5, and that is approximately 1000 ohm, and from that we this from the characteristic RL derived, putting the all these value we get the output at impedance corresponding to 500 kilo ohm, I mean in this relation, and typically for putting all these value we get the given output impedance 500 kilo ohm, and based on the value on example characteristic of the common emitter can be summarized as large current gain 100, large voltage gain 200, and power gain to 20,000, and input output phase shift is 180, input impedance 1 kilo ohm, and how high output impedance is around 0.5 mega ohm. These are the some of the typically unsolved problem which you can work out in the same way for the amplifier, and these are the references which we have used for the developing this lecture material, and thank you very much.